here. So are we going to do the group activity today or tomorrow? It will be on Wednesday. Yes, the group activity will be on Wednesday. So today we're going to focus on finishing up the rest of Module 2 slides about nomenclature. And then after that, we're going to go ahead and on whatever we don't finish today, we're going to do at the beginning of class on Wednesday. And then we're going to do the group activity. I will upload the group activity to Canvas that morning. You don't have to have a physical copy, so you can have a physical or a digital copy. Just bring something that you can actually see it with to the activity so that you can share, somebody can share their screen and you can work with it as a team, okay? So that's the key there. So it will be released on Canvas probably tonight or a Wednesday morning at the latest, okay? So yeah, I'll probably do it tonight since I have to do it for my other class as well. All right, also don't forget homework is due tonight at midnight unless you've made other arrangements already. So go ahead and remember, use Canvas as your guide to figure out what's due, when's due, and what lectures we're having today. So if you pulled up Canvas and looked at our lectures for today, it was going to be the rest of nomenclature. And so, then it also shows us that on Canvas, that lecture schedule also shows that we have our activity on Wednesday. So that's without further ado, let me go ahead and share my screen with my iPad here. iPad. Let's see, is it gonna do it? Yes, it is. All right, so I just need to find where one of these screens is. One of the screens with all the people on it disappeared. Not that one. So it's the lower one. There it is. There you are. Okay. So, all right. So now I can see the gal review up here, and I do have access to the chat. But what we're going to talk, where we ended up last time, we talked about bicyclic compounds. And the bicyclic compounds have to do, had a special naming system other than with the others, where we wanted to put the brackets in the middle of the name to tell us where everything was. So we counted the total number of carbons in the bicyclic compound. That gave us our hydrocarbon name, octane. We had to say that it was bicyclo, but then we had to say how many carbons were in each bridge. And we went from the highest to lowest, which is unusual, with dots in between. So when we do this, we also want a number from a bridgehead carbon. And so that's one of these right here, bridgehead carbon. And let's go to red, a bridgehead carbon starting from, and then go around the largest bridge, the second largest bridge, and the third largest bridge. So if there are two bridges that are the same size, you'll go around the one with any possible substituent first. So other than that, naming these bicyclic compounds is unique, and it is found on the review on the review sheet in Canvas. So you can review it there as well. In fact, one of these will appear on our activity, so you'll get some practice then. So that gets us into all of the alkanes. So remember what the AN means. AN means that there are no double bonds and no triple bonds. So now we're moving off to the alkenes. Okay, an alkene is any hydrocarbon compound that contains at least one pi bond or one double bond, and it typically has a different general formula. For the hydrocarbon, we had it with a for an alkanes, it was +2. So those were the two at the end of the chain. For an alkene, we lose those two hydrogens to make our double bond, and therefore the general scheme always has this CnH2n. So that's where we get it from. And we're going to change that infix name to -ene. We still use the parent chain for the suffix. The parent chain is always the number of carbons in the chain. But in the case of alkenes, we must include both carbons of the double bond. So that's the subtlety of it. We need to make sure we do that. So let's go ahead and practice that once or twice. So here we have an actual longer parent chain that would have only carbon-carbon single bonds. However, because there's that one double bond, we must have that in our parent chain. So if we start numbering from that parent chain here, and I'm going to choose this, we have to start here. And in addition to that, you want the first carbon of that double bond to be the lowest number, if at all possible. Okay, so we're going to start numbering this way. And if we continue to number in this direction here, we'd end up with 7. But because we numbered in this direction here, we have a total of 8. So that means we have octa for 8, ene for the alkene. And that makes the other chain a substituent. Even though you'd have a longer chain without the alkene in there, you must have the alkene in the parent chain. Okay, so if that takes us into that section, then we have to name the substituent. And our substituent is 4, so it's butane. So that means it's a substituent. So we drop the E and add an L, a YL. So it's butyl. Okay, so that's our substituent right there. And because we're numbering with the alkene carbon at the lowest number, we have to start here and go 1, 2, 3, which means our substituent is located on the 3 carbon. So our final name is 3-butyl octene. However, if that double bond had appeared anywhere else in there, we would have to locate it. And so for precision's sake, what we are doing is we're locating that first carbon in there to give us our full complete name of 3-butyl oct-1-ene. Okay, so the En tells us we have a double bond. It must be in the parent chain, and that 1 tells us where it is. That's the locator. Okay, questions on that? Okay, all right, well, let's get a little more complicated. Right here, we have a bunch of different kinds of alkenes. So if we have an alkene at the end of a chain, that's what we call a mono-substituted alkene, meaning you only have one alkyl group attached to it. Okay. Now, if you don't have it, then it's just ethylene itself, and that's a separate molecule. But for the sake of higher hydrocarbons, we have this substitution pattern right here. So with just one substitution here, we can have that. We have to have that double bond at the end of a chain. Okay. Now, if we put 2 groups onto it, now it gets complicated because we can have both groups on the same carbon. And that means that this double bond is sitting outside of a longer chain. Notice I didn't say parent chain because this has to be included in the parent chain. Then we have it where we have 2 groups are on the same side of the double bond. Unlike alkanes, where you have free rotation around your sigma bond, you do not have free rotation around that double bond, meaning it's fixed in space. And we're going to talk about special ways to name that. And so the simple way of thinking about it is if they're on the same side, we call that a cis molecule. If they're on opposite sides like here, we call that a trans molecule. But those are the 3 possible isomers for disubstitution. Now, once you add 1 more, it actually gets easier because you only have 1 possible way to do that. And tetra, of course, is simple as well. Okay, so those are the different types of alkenes we have. There we go. Now I said there's no free rotation around that double bond. So that means we have to be very specific about how we name it. So we have 2 different ways of naming it. If you only have 2 substituents or 2 of the exact same substituents, you can use what we call the cis trans naming nomenclature right here. So in this case here, we have 2 groups, preferably the same group that are our groups here. And if they're on the same side, notice they're above or not above, next, they're on the same side, they're next to each other, they can touch each other. This is what we call our cis in same side substitution pattern. However, if they're on opposite sides, see how these 2 R groups cannot touch each other because they'll touch hydrogens first? That gives us our trans configuration. So imagine that being the opposite configuration. So we have same side and opposite side. Okay, now this is true because they are fixed in space. There's no rotation. So that means we have what we call stereoisomers. Stereoisomers are attached, have all the same linkages, but they have a different fixed in space configuration. And so we have to identify them as such. And we're going to have a lot more about stereoisomers when we get to chapter 5. Okay. So with the cis isomers, the two similar groups are on the same side, preferably preferably the same thing. And with a trans, they're on the opposite side. And so that works very well for just two substituents. When we use that in the name, we have to find the parent chain. We have to signify where the alkene is, because the alkene is not at the end of the chain. So we have to show where that alkene is. And then we have to add cis or trans to it. Notice when you're typing this, these are italicized. However, writing it, it doesn't really look that way all the time. So if we were naming this, we have 1, 2, 3, 4 carbons. Either way you number it, it's going to be the same. But notice that the first carbon of the double bond is on that 2 carbon. Okay, so we have 4 carbons, so that's butene. We have to know where that first carbon is. So that's where we get butene right here. And now because the groups are on opposite sides of each other, they're trans. So it's trans dash but dash 2 dash ene. Okay, now if we have the other isomer where they're on the same side, we use the same nomenclature where we go 1, 2, 3, 2, 3, 4. And notice the first carbon of the double bond is still on the 2. So, but we have them on the same side. So it's cis dash but dash 2 dash ene. Okay, so that's how we number it. However, it is, if you have more than 2 groups on that system, it makes it cis and trans difficult. Cis means same, trans means across, yes. And so what we have in the case of where we have more than 2 substituents, we actually have a more precise nomenclature system. And we call that the E and Z system, okay. So notice here, if we had the same group on each other, like for example, we have 2 ethyl groups and they continue along the same parent chain, we can still say it is the cis methyl hex 3ene, okay? And here we have the same 2 propyl groups here. And the 2 longest groups are the ones that are trans to each other. However, that can get confusing. So what we have is a more precise nomenclature system where we call it the E and Z terminology. Okay, this will work with everything with 3 substituents and up. Okay, so in the E and Z terminology, we look for the atoms bonded directly to the sp2 carbons and assign priority on each side of the double bond. Okay, so in this case here, let's see if I can't get the camera right off that. There we go. Oh, let me do it this way. All right. All right. No, that's not. I mean, I like having a halo and everything, but I'm sure it's difficult for you guys to see. There we go. I think that's better. Okay, so in the E and Z system, we look at what's attached to that double bond and we prioritize them. So the first step is we have to cut the double bond correctly. So the first thing we do is we make a line right down the middle of the double bond, cutting that double bond in half. So we have 1 carbon of the double bond here and 1 carbon of the double bond here. Okay, so now we have to figure out which group has priority on one side of the double bond, and then which group has priority on the other side of the double bond. So we're going to take this side first, right here. And to assign priority, the first thing we look at is the one with the highest atomic number, not atomic mass, atomic number. Okay, so in the case of here, we have hydrogen as atomic number 1, carbon is atomic number 2. I'm sorry, 6. 6 is higher than 1, therefore 6 takes priority on this side, which means this has priority, this group right here. Okay, so I'm going to erase that off hydrogen there. Now, once we've assigned priority to the first side of the molecule, we assign priority to the other side of the molecule. Okay, so now we come over here And neither one's a carbon, so that's interesting. But we have oxygen right here, which is atomic number 8, and bromine, which is atomic weight 79, which is atomic number, I don't remember, like 40 something, 35. Thank you. I don't have a periodic table in front of me. So we have atomic number 35 and atomic number 8, meaning that the bromine has priority. So this has priority over this. Now, we've assigned priority to the first side. We've assigned priority to the second side. Now we compare those two groups that have that high priority. And in this case, they are on the same side, okay? So we can erase all that because that doesn't matter now. So we have two groups with the highest priority, the highest atomic number, on the same side. So we use the term E if they're on the same side. No, I'm sorry, E if they're on the opposite side. E stands for the German entgegen, meaning opposite. And the term Z stands for zusammen, which means same. So the way to remember that is Z is same side. Okay, so Z is same side. So in this case here, we have the the Z isomer of this compound. Okay, so what we're going to do is we're going to put that Z at the beginning, just like it was a cis or trans. But because we didn't have similar groups, the E and Z terminology is much more precise. Okay, so let's do that again, right here. Now, if you can immediately find the difference between the two groups with just looking at the atomic number, that's great. However, sometimes you have extended chains and you actually start one out and there's two carbons attached to that carbon of the double bond. And then, well, they're the same number, right? So what do? Well, then you go out from there and you continue out until you have a difference. Once you have the difference, you assign priority. Okay, so it's the same process. You just keep going out and out until there is a difference. So let's do that example here. So over here, we've replaced, it's the same molecule. We're going to do the same thing. We're going to split it in half down the middle here. And we're going to look at one side first and then the other side. So this side's easy, right? Because bromine, we already know, is a higher atomic number than oxygen. So it has priority. Okay. However, let's go to the other side. Okay. So we look at the ones that are attached to this carbon right here, and we have a carbon and a carbon. Okay, those are the same. So we need the tiebreaker. So we go out one more. We go out to here, and we have a carbon with 3 hydrogens, and we have a carbon with 2 hydrogens and another carbon. Okay, now we have a difference. Okay, attached to this carbon here, this one only has 3 hydrogens. Those are 3 low atomic numbers. Over here, we have 2 hydrogens, but 1 carbon. That's the higher priority number. That's the higher atomic number, and therefore that gives it priority on this side. Okay, so if you do not see differentiation in the atom when you first go over, continue out further and further. And another way to look at that is to look at the things that are attached. So for example, if we look at this carbon and this carbon, we have 1, 6, which is this carbon, and a 1, 1, but we have the exact same thing on the other side. However, if we go to the next side over, what we end up with is 3 1s and a 6 and 2 1s, giving it the higher priority. So that's another way to look at that same thing, but what you're doing is you're looking for the first differentiation between those same element numbers. All right, questions on that? So the true assignment on this would be Z. They're also on the same side. Okay, so let's move on with that. All right, any other questions about E and Z and cis and trans? Cis and trans is best on di-substituted compounds. E and Z is best on all other. Z is same side, which is still this equivalent to cis. E is entgegen, opposite sides, equivalent to trans. Yes. There was a question in the chat. Okay. So Now we can name any compound unambiguously. Just make sure that both carbons of that double bond are in the higher atomic mass gets priority. Yes. So, no, not atomic mass. Sorry, higher atomic number. There are two. It's atomic number. Yeah, sorry. There are a couple elements that break that rule, so we actually use atomic number, not atomic mass. Okay. All right. Okay, hang on. Yeah. Okay, go ahead.
Okay. Hi, Professor. I have a question. So the reason why I put higher atomic mass is for the second portion where C has 2 hydrogens and 1 carbon, and then on the other side it's 3 hydrogens.
Right. But the key here is that carbon has a higher atomic number than the hydrogen.
Okay, for the H2.
Yeah. Once we get to this section here, notice we had, if we looked at all the atomic numbers here and here, they're all the same. It's a 6-1-1. This is a 6-1-1. If we looked at all of the atoms there. So what we're saying here is that they're equivalent. There's no differentiation yet. Over here, we have atomic numbers 1-1-1 and atomic number 6-1-1. They now have a differentiation, and this becomes our higher priority. Does that make sense?
Yes, because of the carbon.
Because the carbon having a higher atomic number.
Okay, thank you.
Okay, great. Good question. I like when we can clarify things like that. All right, so now we have alkenes. So what if we have a triple bond? Well, that changes the infix one more time. We go from that ENE to a YNE. So these are hydrocarbons, and I'm gonna draw attention to this last E. If you only have hydrocarbons, only carbons and hydrogens, you're gonna have an E at the end of your name, okay? Because that's its chemical class. The YN is the fact that we have at least one triple bond between 2 adjacent carbons, okay? And when we make that second double bond, second pi bond, we lose 2 hydrogens. So our generalized molecular formula now becomes CN H2N minus 2. That's how we get the second double bond, okay? And these are all with the suffix "-ine". Now, just like with alkenes and alkynes, the parent chain is the longest continuous chain that contains both carbons of the triple bond. Not just one, both. Of course, it kind of has to in alkynes. It didn't have to in alkenes. So we're going to do that again with this. Obviously, this is just like the alkene example, where we would have a longer chain if we did this. However, because it's the triple bond is changing the name with the YN, we must include it. So we cannot do that as our numbering system. So we have to number from our alkyne without our longest chain, which gives us a total of 8. So, okay, I'll explain that. All right, so in this case, we also want to have if the triple bond is not on the end of a chain, we want to have it the lowest number possible. So that being said, we're going to number from this side up, giving us our 1, 2, 3, and we have our octyne. So our name should be octyne with our butyl substituent. So because that's a substituent, it's but for 4 carbons and YL for being a substituent. And so we have it located on the number 3 carbon. So it's 3-butyl oct. And if it was anywhere else, we would have to note where that first carbon of that triple bond is. So because of that, we're going to use the -1-ine. Okay. When these double bonds, the triple bonds end up in the middle of the chain, we'll note that by the first carbon in the triple bond. Okay, so that sounds very familiar. We're following all the same rules for alkanes, except that we must include the double bond or the triple bond. Okay, well, what if you have more than one? I mean, we just did an example. It has to have at least one. Well, If you have more than one double or triple bond and they're the same thing, so like let's say you have two double bonds, you can actually use the term diene, triene, tetraene, depending on how many double bonds you have. You just need to make sure you locate them, writing the number of the first carbon on each of those double or triple bonds where they are, okay? So you can do this with alkynes as well. So it'd be a diene, triene, tetraene, okay? So the key here is that both or all of the double bonds need to be, all of those multiple double bonds must be in that continuous chain. So let's try one of those, for example, right here. So in this case here, we have two alkynes in a long chain, okay? So we need to find the longest possible chain containing all of the alkyne carbons. And turns out we are going to start at this end, and if we went to here, that's it. So we have to go to at least here because we're including all of the alkanes, all of the alkynyl carbons right here. And that turns out we can go to this side or this side, and it'll give us the same total number of 7. So that would be heptyne if we only had one double bond, triple bond. But because we have two triple bonds, we have heptadiene, okay? And we have to locate exactly where each of those are. And if we look at this here, we see that 1, that's the number, gives us the lowest number. Notice if we numbered from the other side, the substituent would be on the lowest number, but our first double bond carbon, triple bond carbon would be on the 3. That's why we don't number it that way. We number the double or triple bonds first at the lowest number possible. So that's why we have the substituents we have and where we have it. So this is our 1 position. And then if we go over here, the 4 carbon has the first carbon of our triple bond, okay? That's why we have in our name hepta 1-4, 1,4-diene. So that's the 1 carbon of the diene, that's the 4 carbon of the diene, and that's how we make sure we know exactly where they are. Now we have 2 substituents. They're both the same. We have a methyl group here and a methyl group here, so we have dimethyl. We just need to locate them correctly on the number 3 and the number 6 carbons. Okay, so that's why we have dimethyl, and they're located on 3,6 dimethyl hepta 1,4 diene. Are the methyls groups need to be on the lowest numbers as well? Now, if the dienes were not there, we would renumber this such that those methyl groups are on the lowest. But the alkynes and alkenes take precedent. The carbons on the alkenes and alkynes have to have the lowest number. So that forces to number it only in one direction, with the alkyne having the lowest number. So that's why the alkenes and alkynes, you always want to have the double bond or triple bond carbon at the lowest number. Okay? And that's why these dimethyls seem to be coming at a different location. Okay? Did that answer the question in the chat there? Okay. All right. So what if you have double and triple bonds? Okay, well, because you have a hydrocarbon that has a double bond, you have to signify that it's there. And because it has a triple bond, you have to signify it's there too. So you have to call it an ene, saying that you have an alkene, a double bond, and an alkyne in the same molecule. So we have ene, but we also want to locate them, and we want to locate them such that the double bond is lower in number. Okay, think of it this way. Ene, you want to identify the ene first as the lowest number, and then the ine follows. Okay, so when we're looking at our parent chain here, we only have 7 carbons, and we have no other branch points, so that's great. So we have hepta, but we have an ene. And so by numbering from this direction here, our alkyne would have the lower number, so we're not going to do that. We're going to number from the other side right here. We have 1, our alkene is on the 2 carbon, and that gives us our alkyne on the 5 carbon. Okay, so that gives us hept-2-ene. Now we have to identify where for the alkyne is -5-ine. Okay, but we have a double bond, so we have to say stereochemistry. So in this case right here, our stereochemistry for the double bond is, oh, the 2 groups are on opposite sides from each other. So they're on opposite sides from each other. They can't butt into each other. So that gives us the trans. So that brings our total name up to trans dash hept-2-ene -5-ine. Yeah, don't try to say that in a drinking game anytime soon. Okay,
Wait,
yes.
you said it was trans, but can you draw again where we're referencing the opposite groups from?
Okay, so let's do it in blue here. Okay, so here's the double bond of interest, right? That's the double bond we want to play with. And this group is on the other side of the double bond from this group, okay? Remember, we only use cis and trans when we try to when there's 2 substituents on our alkene. And so we have one facing in this direction, one. So see how this is on the opposite side of the double bond from this one right here? Now, if we had the other isomer, let's say we had it where this methyl group was over here instead, right here. So now this group is on the same side of the, okay, how about if we drew an axis along this double bond right here? Okay, so if we look down the double bond right here, cis and trans tells us we're on the same side of that axis right here, cis. And if it was over here, we now have the blue on one side of the axis and the red on the other side of the axis. Is that clearer for you?
Yes, so
Okay.
even if there's an alkyne present, we name cis and trans based off the alkene.
If there are 2 things on an alkene anywhere in the molecule, you have to name cis and trans. Alkynes don't have cis and trans because they're linear, so we don't care about those, but alkenes do. Okay.
Okay, yes.
So now I say this axis for cis and trans only because remember, when we do the E and Z, we actually cut the double bond in half. So be very clear about that. That's why I avoided the term, but if we look down the double bond, we have cis and trans. If we cut across the double bond, we have E and Z. Okay? Be very clear on that. All right? Okay. So let's see, that's everything there. All right, so that's the last of our hydrocarbons. Now we're going to move to compounds that have things other than carbon and hydrogen on them, okay? And so in the case of hydrocarbons, alkanes, they have very little reactivity. We have very little polar groups on there. The bonds are almost nonpolar. With the alkenes and alkynes, we have that double bond. That double bond is more reactive and is probably going to be the thing that reacts first. However, once we move to other atoms, we have a bunch of different configurations for how those can be on. And because they tend to have polar bonds or the bonds that actually do chemistry, we call them functional groups, okay? And we have a wide variety of functional groups to work on. Note, this semester, we're only going to go up to aldehydes and ketones. All of the carboxylic acid derivatives shown here, we probably are not going to get to this semester. And these are also found in the second half, okay? But it's helpful to start, looking at what they are and memorizing. So all the other ones, these are not required. All the other ones are required knowledge for naming and understanding, okay? So I'm going to go through each of them one by one. The first one we're going to have is an alkyl halide. That means we're going to have a halogen on there. Fluorine, chlorine, carbon, or bromine. Iodine or bromine, okay? And we'll see that that actually doesn't change the name. It's named for the parent hydrocarbon. We have alkenes and alkynes, which we just looked at. Those are functional groups too. Those are the things that are going to react. So notice alkane wasn't on here because that's not a functional group. By adding an oxygen to the system instead of a carbon, we've now changed the chemistry, and we call them alcohols if they have a hydrogen on the end. And if you have an oxygen with bound to two different carbons, it's called an ether. And if we have a sulfur there with a hydrogen on it, it's a thiol. But if we have a sulfur with two carbons on it, we call it a sulfide. Now, we're not going to talk about these aromatic compounds until next semester, but I want you to know that that can act as a substituent on our system. And we call them as a substituent always in this first half of the chemistry. And then the next two functional groups involve this C double bond O. That C double bond O is a polar group. It's a polar bond, and it gives lots of functionality to our system. If you have it bonded to two carbons, it's a ketone. And we'll talk about how we name that. If we have it as an aldehyde, we have it bonded to at least one hydrogen. Okay, so that's the differentiation between the different functional groups we're going to go through. And again, we're going to learn how to name these, but you don't have to know these for a while yet. Okay, so we have all these rules now, right? We have these rules in our order about naming things and nomenclature. And if you go to the thing on the Canvas site, it actually has a step 0. Step 0 is identify the functional group, okay? Because the functional group actually names the compound, and it's by the priority of that functional group. So, and I want to blow this up real quick here. So alkanes is our simplest thing. So if it's just a hydrogen, or it's something with an alkyl group or an ether or that, these are all substituents, and it's going to say AN, ANE. They're just alkanes. Once we go above that, an alkyne is a higher functional group than an alkane, so that we're going to name it for the alkyne. And an alkene is a higher functional group than the alkyne. That's why we say it's an ene. Ene comes first, it's higher priority. Okay, the first substituent we can add that changes the name of something is a nitrogen, and it's called an amine. And so we're actually going to end up dropping this little E at the end and adding words to the ends of these things. Then we have an alcohol, the aldehyde, and the ketone system right here. And then all of these are higher. So that means if you have a carboxylic acid or carboxylic acid derivative anywhere in your compound, it's probably going to be named for that. Okay, so the key here is to look for, find order in this prioritization to know how to name it. So let's say we had something with an OH on it, right? Okay, I know my functional group is an alcohol. That means it's going to be named for it. That means I need to find my longest parent chain with that functional group. Okay. Now, if you had an alcohol and a nitrile on here, you have to name it for the nitrile, and the alcohol becomes a substituent. Notice that if it's a substituent, it has slightly different names. The thiol is sulfamyl. An alcohol becomes a hydroxy substituent. A carbonyl becomes an oxo substituent. So that's a key difference here, is that these are the lower priority version of that group, and these names at the end signify it's the highest priority. So we're going to work through a few of these, and so you get the hang of it. But the idea is you always have to name that principal functional group first, and then find the chain. Okay, so what that does to us is that breaks all our names down into the substituent, which is in the prefix of the carbon chain, which tells us the number of atoms in the carbon chain, the infix, that tells us whether we have single bonds, double bonds, or triple bonds, and then the suffix tells us the highest functional group. And so the end of the word name changes. Okay, so let's start off with something. If we had an alkane right here, if we didn't have this on here at all, we would end up with 1, 2, 3, 4, 5, 6, 7, 8, 9. So we would have non-name And we would have, if we didn't have this group on there, it would be 5-ethyl nonane. And there's an E at the end here, okay? But we have that nitrogen on there. That nitrogen is the first group that changes the functional name of the thing. So we ended up having to make that part of the parent chain. So that means our parent chain has to be this one right here. Instead of the nonane with an ethyl group on the side, we now have our, and again, we're going to try to put our functional group at the lowest number. 1, 2, 3, 4, 5, 6, 7. So now we have heptamine. So when we wrote, if we wrote it out as a hydrocarbon, it'd be hepta. It'd be heptane. But because we now have the amine on there, we drop the E and add amine to the end. And now we have to locate our group here. So we have 3-butyl, and then it runs into heptamine. So we're going to drop that A in and add amino, heptamine. Okay, so now let's extend that out to naming even more complex. Okay, actually this looks like it's out of order. That should have been with the double. Okay. Oh no, okay, there it is. Okay, so if the possibility for more than one parent chain exists, and you can choose a parent chain which contains the number of double or triple bonds, you always do that. Even if you can find a longer chain, you put as many functional groups on that main chain as possible. So our main chain becomes the diene now, and that tells us that we can have a 6-carbon chain on that, which leaves everything else as a substituent. Now we have to number these, of course. If we numbered from this side 1, 2, 3, 4, our substituent would be on the 4. But if we numbered 1, 2, 3, our substituent would be on the 3. Now notice, because both of the alkenes are at the end, we can number from either side, but we have to include both of them in that name. So that's what gives us our 3-propyl hexa 1,5-diene. Now, just like before with hydrocarbons, if you have 2 chains with a possible maximum length, you want to pick the one that has the greatest number of substituents. And notice that we have to use the part that has this amine on it because that's changing the name. So it's changing it to hexamine. And in this case, we're signifying this on the 1 carbon. So that means we have 1, 2, 3 substituents on our 1, 2, 3, 4, 5, 6 carbons. So we have 6 carbons to here. We have a methyl group on our 5 here, a methyl group on our 3 here, and a 1, 2, 3 butyl group on our 2. So you end up with 2-butyl, 3,5-dimethyl, hexa 1-amine. Okay, so we found the highest priority thing. In this case right here, the highest priority was the alkene. Then we had to make sure both of those alkenes were in the longest parent chain. And we found the lowest number for the substituent. Here, we see that the amine changed it. So that amine had to be on the parent chain. And just like before, we're trying to get the greatest number of substituents on and the longest chain possible. All right, questions on that? Okay. So the third thing we need to do when we're trying to step these up is that if it's anything other than a hydrocarbon, we're going to drop that last E. That E technically means hydrocarbon. It's just kind of a placeholder. And therefore, we drop that E and we add whatever the functional group might be. In this case here, we're going to take something and add the carboxylic acid, the highest priority functional group. Now, whenever we have a carboxylic acid, we drop that A and we add oic acid to the end of it. Okay, so we also have to number our parent chain with the carbon of the carbonyl first. Okay, so in this case here, we have a carboxylic acid, and therefore we must start numbering from there, and we must find our longest chain. So over here we would have a 5, but we we would have this weird substituent. So we want to actually renumber such that we have the longest possible chain with the substituents. So it looks like we're going to actually go in this direction. Notice that this one would give the equivalent number here, but we're going to we got to make a choice somewhere. So if we do it that way, that means we start with our carbonyl, we start with our carboxylic acid carbon and number out, so we get a total of 5. And so that gives us penta, right? So that penta, we're going to lose the E and add oic acid. So it's pentanoic acid right there. And then now that we know that pentanoic acid is our parent ion, our parent, we locate our substituents. We have a butyl and an ethyl here. And so we're going to, a propyl and an ethyl here. And so we're going to list those alphabetically and then put the correct number location on. So this ethyl group is on that 3 carbon, so we have 3 ethyl. This propyl group is on that 2 carbon, so we have 2 propyl, pentanoic acid. So this is the first time we started dropping that E, is because of the functional group at the higher priority than a hydrocarbon requires us to do this. Okay. So our fourth one is we want to number the parent chain to nearest the functional group. So in a carboxylic acid, it's always the carbonyl carbon. For an aldehyde, it'll always be the carbon. Where did he get the propyl group from? These 3 carbons right here that make up this substituent is the propyl group. And that propyl group, 3 carbons, are attached to this number 2 carbon. So that's where we get the 2 propyl from. Okay? So, all right. All right, so just like before, we're trying to get the whatever that's named for at the lowest number, right? And then of course, you want to, in this case here, we have a C double bond O, and it's bonded to 2 different carbons, which gives us a new functional group, our ketone. Okay, cool thing is that one is also what's going to end up being at the end of our name here. So that's an easy way to remember. Aldehyde is going to end up with aldehyde is actually going to have an AL at the end of the name. So that's easy to remember too. Okay, so let's talk about our ketone. We want to have our functional group at the lowest number, which means we have to number from this direction. Doesn't matter how many substituents we have, you have to number the primary functional group first. Okay. So that means that we have to number from that direction. So we have an unambiguous naming system. We're going to number from this direction over, and we have our 3 is where our ketone is, and we have a total of 8 carbons in our longest chain. So we have octane 3-one. So we showed it's a ketone. That ketone is on the 3 carbon. We have 8 carbons in our main chain, and we have 2 substituents, an ethyl group on the 5 carbon and a methyl group on the 7 carbon, giving us 5-ethyl-7-methyl octane -3-one. Octane. Notice there's no E there. Octane -3-one. Okay. Now, in the rare occurrence that your functional group, like this alkene, is going to be the same either way, you always then you use the lowest substituent rule. But if the functional group comes first, and if there isn't a clear distinction in the functional group, you then do the substituent rule. Okay, so that's why this is on the 3 carbon, and our alkene is located on the 4. It'd be located on the 4 coming from this direction or this direction, so that means the substituent takes priority.
A question.
Yes.
For the 5-ethyl-7-methyl, we're still doing this substituents in alphabetical order. That's why you did ethyl first.
Always do substituents in alphabetical order, regardless of the number. The number just tells us where they are.
Okay, thank you.
I also have a question.
Yes.
Like for the first one, it has like the methyl octane instead of octane, and then for like the second one, it has the ethyl oct. How do you know like whether to put octane?
Well, because in this one right here, we have the AN is telling us we have an alkane. There are no double bonds, there are no triple bonds. Okay. In this one, the ene, the EN is telling us we have an alkene. So it changes that infix because the prefix tells us the number of carbons, the infix tells us the types of bonds we have. Ane is only single bond, ene is at least one double bond, ine is at least a triple bond. Okay, so that's why there's no A there, because the A is actually from being an alkane, but this is a higher priority naming group. Okay, but in this one we have an alkene, and so that has to be in the name as well. In fact, the alkene is the priority naming group in that particular compound. Does that make sense?
Yeah, thank you.
Okay. And of course, if we look down the axis, because we only have two substituents, we have them on opposite sides of the axis from each other, which gives us trans. Okay, so now let's add another rule. Okay, if numbering from either side of the chain, we can give the same parent, and then we go to and it gives the same substituent number, you actually give priority to the lowest alphabetical order. Okay, let me describe that here. So if we numbered from this side here, 1, 2, 3, our first substituent is on a 3 carbon, 4, 5, 6, 7, 8, 9, and 10. Okay, so in red, our first substituent is on the 3 carbon, and our alkene, which is what we're naming the compound for, because it's an alkene, is on a 5. So, and if we name it in blue, the alkene, which we're naming it for and has to be the lowest number, is also on a 5. So neither direction says which way we can number it. Okay, now if we go in the red naming right here, we have our first substituent on a 3. We have on blue, our first substituent is a 3. Okay, so we have the first substituent would be on the same carbon, whether we labeled it either way. Now, are they exactly the same? We have a methyl group and an ethyl group. Okay, the differentiation here is now we pick the ethyl group as our lowest number substituent because of alphabetical order. Okay, so that means we must use the red numbering system because the ethyl group will appear on a lower number than the methyl groups, and it will still give our alkene on the same number, number 5. Okay, so we have 10 carbons, which we dec. We have the alkene on the 5 carbon, 5-ene. We have 3 methyl substituents, 1 ethyl substituent. So the ethyl substituent is our 3. So 3 dash ethyl dash. We have methyls on the 4, the 7, and the 8. Trimethyl, dec 5-ene. And our double bond is trans, so we add that at the beginning. So what you can easily do is just break it down into each little thing and make sure that they're all present and accounted for. And once they are, you can build the name from there, saying, okay, dec 5-ene, look at my substituents, make sure they're in alphabetical order, and then add the stereochemistry last. Okay, so it's just following the process every single time. And we're going to have, our activity is going to show us exactly that. Okay, so now when we have cyclic compounds, remember when we talked about just cyclohexane, the first substituent was at the number 1 location. However, the functional group also acts as as the lowest number. So if the functional group changes that name, that is your number 1 position always. Now, if you have substituents and only 1 substituent, you're going to number it so it's the lowest number possible. If you have 2 substituents, you're going to locate your first substituent first. So the first rule is lowest number possible. So in the case of this cyclohexanone, see, it's got a ketone in it, so it's hexanone. If we number in this direction here, our methyl group is at the lowest number. If we number it all the way around the other way, it'd be in a 5. So we're definitely going to number in that direction. However, now that we have 2 substituents, we want to locate on the lowest one. Look, there's an alkene here. That counts as a functional group. And so we have to have our ene in here somewhere. And so we'll want it from the ketone is number 1, the alkene is number 2. So it's cyclohex 2-enone, ketone, alkene. And then we locate our last substituent, which is this methyl group here. However, if we have 2 substituents that are of the same priority, they're both alkyl substituents, we go in alphabetical order and try to get the lowest alphabetical order at the lowest number. So that's why the 3-ethyl and 5-methyl for the cyclohexanone, because if we named it the other way, the methyl would come first and that would do it. So rings are kind of crazy. You got to make sure you number them both ways to see which way you can get the lowest number on the lowest alphabetical order material. For this right here, because it's fixed in space, you do not have to put cis or trans. Most rings, if it's 6-membered alkenes, cannot have a trans isomer. They're too small. You can't get to a cis or trans isomer until a cyclooctene. So let's put all these rules together. We're going to find on the first one the highest priority functional group. We have an alkane, so we're going to have AN somewhere in the ring. We have no double bonds. We have an OH, but we have a carbonyl, a C double bond O. The C double bond O is higher priority than the OH. That makes the OH a substituent. Okay. So since the carbonyl names our compound and it has carbon on either side of it, it's a ketone. Okay. So we have to measure our longest parent chain through that ketone. And so we get a total of 1, 2, 3, 4, 5, 6. Oh no. There we go. So we have 1, 2, 3, 4, 5, 6. So we're numbering it from this direction here. And our ketone has to be located. So we have hexane. The AN is because we have a hydrocarbon, no double bonds. The 2 tells us where the carbonyl is, and the one tells us a ketone. So that means our methyl group is on this substituent, and our hydroxy is on the 6. Okay, so H comes before M, so our final name is 6-hydroxy. Oops, sorry, I thought I muted my launch. There we go. So again, alphabetical order. So we have 6-hydroxy-4-methyl hexa-2-one, hexane-2-one. Okay, so let's follow those rules again. In the case of the cyclic compound here, we're going to number it in this direction because that's the first substituent. Okay, so our numbering goes in that direction because it's our first substituent. So that means our numbering in this direction, this counterclockwise. So let's locate all of our substituents. We have a 2-hydroxy, we have a 3-ethyl, we have a 5-bromo, and we have a 4-propyl. Okay. So the numbering was fairly easy because it was our first substituent. Now we have to alphabetize them. So the final name is going to be, let's see, bromo, ethyl, hydroxy, 5-bromo-3-ethyl 2-hydroxy-4-propyl cyclohexanone. Oh, let me pull the name up. Cyclohexanone. Okay, we use the same rules every single time. We find the highest priority group, we try to get the smallest number, and then we alphabetize the number if possible. Okay. So we're just doing those same rules over and over and over again. And you can apply this to any compound. Okay, now let's talk about things that don't change the name of the hydrocarbon, okay? Things like the nitro group or the substituent we call the benzene ring, which we call the phenyl group. These do not change the name. They are still alkanes. They still have the ANE at the end. So what we do is we always treat them as a substituent, and then we just try to find the lowest priority possible. Notice that the nitro group and the phenyl group are always the lowest priority if there is another functional group here. So notice the methyl group here on this chain is a higher priority than the nitro group. So the methyl group is at the lowest number, in this case 2. So we have 2-methyl, 6-nitroheptane. Okay, and here on again, the phenyl group is a lower priority. So you actually start numbering from this direction here, which will give us the octane as our main parent. And we have 2-methyl, 8-phenyl octane. Another way to remember that, might be that we could also, in both of these cases, do them alphabetically. But again, they are your lowest priority groups. They typically come at the end. Okay, so now I'm going to go through each of the functional groups and how to name them individually. Okay, so the first functional group we're going to talk about is the alkyl halides. Again, it's still going to be an alkane, an alkene, or an alkyne, but it's going to have a substituent that's a halogen. And the halogens are, fluorine, chlorine, bromine, and iodine. And we have a special way of naming them because they change reactivity on how we do this. How do you know it was a phenyl ring? Anything that's the benzene ring, the six-membered ring with alternating single and double bonds, that's the benzene ring, and that's our phenyl substituent. So in the case of our alkyl halides, if the carbon is attached directly to the halogen, we call that the alpha carbon. And if there are hydrogens attached to that carbon, we call those the alpha hydrogens. Okay, so that means that the bromine right here is controlling the reactivity of the system, which means the carbon it's attached to is the most important and is the alpha carbon, and any hydrogens next to it will be the alpha hydrogens. By going over one carbon over, so now we're not on that primary right here, we're now on the one bond away, we call those the beta carbons and the beta hydrogens, okay, or beta protons, okay. And if you go one more over, they're gamma. And the reason is their interaction with what's happening is very different on how we're going to use them. For example, in some reactions, we're going to use these beta hydrogens are going to be the most important hydrogens that we're going to use. So we need to identify them correctly. Bound directly to the carbon with the halogen are the alphas. One carbon over are the betas. 2 carbons over are the gammas. We also have classification based on the classification of the carbon. For example, if your halogen is on a primary carbon, right here, there's only one other carbon bound to it, this is a primary halide. In the case of this one down here, this is a secondary carbon because it has 2 other carbons bound to it. That's a secondary halide. And in the odd case where we had a tertiary 3 groups on that carbon and a halide here, this is what we call a tertiary halide. It's important to identify them as primary, secondary, and tertiary because they have different reactivities. Okay. All right, so when we name alkyl halides, again, they don't change the hydrocarbon name. They only act as a substituent, okay? So alkyl halides, alkyl groups, and ethers all have the same priority and all act as substituents, okay? If we have a double or triple bond, we need to make sure we include the EN or the YN in it. And when we have those, you try to get the first substituent as the lowest one. And then in this case here, if we number from either side of this chain, we're going to get a substituent at 2 and a substituent at 2, then we have to use the alphabetical order one, which means the bromine is going to be lower than the methyl group here. So lowest substituent, if they're the same from both sides, we go in alphabetical order. Okay, so that makes this the 2-bromo dimethylpentane. Okay, 2-bromo 3,4-dimethylpentane. In the case of a multiple bond here, we know we're changing it. We have to locate that. We use the rules for locating the double bond first. That tells us our substituent is on the 3 position, and we have pentene. Okay, so we have 3 substituents on there. We have to do our E and Z rules. Okay, remember in the E and Z, we cut the molecule in half first. We find priority on one side first. And in that case, it's this carbon here because we have an assumed hydrogen. And on the other side, we have a bromine and a carbon. Bromine wins, so that makes the priority on this side. So these are on the same side of that double bond, which makes it the Z isomer. So here we have the Z. Notice it's in brackets. It's not just italicized, but it's also in brackets to make sure. 3-bromo-pen-2-ene, because the alkene is on the 2 carbon. So the bromine is just a substituent, but we follow all the other rules. And again, they're the lowest priority. So if there's anything else naming it, it is going to be just a substituent. Okay, the next functional group we have that doesn't change the name of the parent chain is the ether. And so an ether is where you have an oxygen with 2 carbons bound to it, 1 on either side, right here. So if you have carbon and carbon, that's an ether. But if you had a carbon, oxygen, hydrogen, that's an alcohol. And that changes the name. We're not talking about that. So the way we look at that is we find the parent chain, which is the chain that has the longest number on it here, and then the O with the other alkyl group becomes the alkoxy. So if it was just an alkyl group, it'd be the alkyl substituent. When it has the oxygen on it, it's called the alkoxy substituent. And so we're going to use the number of carbons in that chain, but we're going to add the word oxy to it. Okay. So in the case of this ether down here, okay, in the case of this ether down here, our longest chain is this 4-carbon chain. So we have butane. And the other part of the chain is the substituent. There's a total of 2 carbons. So we have F for 2 carbons and oxy for the fact that it's that ether configuration. And we locate that somewhere on the parent chain. In this case, it's the 1-ethoxy butane. So again, alkyl halides, ethers, and alkyl groups are all substituents on that parent chain, and our parent chain stays the priority. So cis and Z are where they're both on the same side of the double bond. Z is if you have more than 2 substituents. Cis is when you have 2 substituents. So when we look at alcohols, we also have the same priority system we had with the alkenes, with the alkyl halides, where an OH on a primary oxygen is a primary alcohol. And an OH on a secondary oxygen, carbon, is a secondary alcohol. And an OH on a tertiary carbon is a tertiary alcohol. Okay. So knowing what your primary, secondary, and tertiary carbons are very important. Okay. Now, if there's no other functional group on there and OH is your principal functional group, you drop the E at the end from hydrocarbon and replace it with OL. So if we had hexane, we're going to call it hexanol. But that's, again, we have to think about that infix, that ANENYN still is going to be there. Okay, so don't forget that. If there's even a single double or triple bond, we're going to have that AN, or that EN or YN in the name. Okay. So in this case here, we're going to have to, because we're naming it for the alcohol here, the alcohol functionality has to be on the main chain. Okay, so we can't just call it a substituent. It's now on the main chain because it's naming the compound. So, goodness. Oh, we're not into radicals yet. Wow, jumped way up. All right, there we go. And so we want to pick the longest possible number. Notice because OH is naming the compound, we have to make it the lowest number. The OH changed the name. It's at the end. It has to be at the lowest number. Okay. If this OH was not here, then we would actually number it the other way such that the alkene is the lowest number. But the OH takes priority. So it's going to have to be there. So we're going to have to number from this direction. That controls which way we number it. We have a total of 6 carbons, which gives us hexane or hexanol. But wait, we have a double bond. We have to include that ene in there. And that ene starts on carbon number 4. So we have hex -4-ene -3-all. So this is telling you where the OH is. This is telling you where the double bond is. And this is telling you the number of carbons in the parent chain. Now we have 2 substituents, 1 and 2. And so that gives us a total of 4,5-dimethyl. Notice that I didn't signify E or Z on this one. Okay. There's no difference between this carbon or this carbon, so we cannot identify a priority. Therefore, this does not have an E or Z designation. Okay. If they're exactly the same, there is no E or Z. All right, few minutes left here. All right, so now the biggest variety of functional groups come with the carbonyl compounds. The carbonyl group is that C double bond O. It's the biggest variety you can have. You can start it with just carbon and hydrogen, and you have the aldehyde and the ketone. An aldehyde has at least 1 hydrogen to that carbonyl compound. Ketones have at least 2. That means your aldehydes can be at the 1 carbon, but your ketones, the lowest number they can ever be is 2, and they can be anywhere in the chain. Okay. So those are the basic ones right here. So this is with carbon and hydrogen only. Okay. All of these have some other electronegative atom: oxygen, nitrogen, halogen. So these are all the ones that have more electronegative action: oxygen, nitrogen, halogens right here. And so that's why carbonyl compounds have the widest variety of functional groups available to them, because of the way they bond. Okay. And the 2 simplest ones, of course, are aldehyde, which is signified by an Al at the end of its name, and the ketone, which is an ONE at the end of its name. Okay, so let's name aldehydes. Okay, since aldehyde does take priority out of your alkane, you have to drop the E and add Al. Okay, now because it takes priority over the hydroxide, we are naming the compound for the parent's number of carbons in the parent chain that contain the aldehyde. And the aldehyde starts the numbering at the lowest number. In this case, aldehydes can start at 1 because the other bond to it is hydrogen. So that's giving us hexanal. Hexanal is just our parent chain. Okay. Now let's add our substituents. First substituent's an ethyl, second substituent hydroxy. E comes before H. Therefore, our total name is 3-ethyl-4-hydroxy hexanal. Okay, so we drop that E, added Al at the end. We know that we have an aldehyde. That's the joy of these really specific name structure, is that looking at there, you know, oh, it's an aldehyde. I know exactly where that aldehyde is. I know exactly where the hydroxy is, and I know exactly where the ethyl is. So with ketones, we have ONE at the end of the name. And again, we want to locate it because it changes the name. It has to be at the lowest number possible. And in this case here, that makes us number from right to left. We also have an alkene. So we know we'll have a 4-ene somewhere in here because it's on our 4 carbon. We have a bromine, which is a substituent. So our total number is 5. So we have pent. So we have pent 4-ene, and the ketone is on the 2 carbon, so 2-one. And then our substituent halogen is on our 3 carbon, 3-bromo. Okay. See how all these rules are always used in the same way, and we get to the same answer each time. Okay. Carboxylic acids are the highest priority. So anytime you see a carboxylic acid, you're going to have that oic acid or that oic acid derivative name on them. If it's a carboxylic acid like this, that is the highest priority. It takes priority over all the other other functional groups that are similar, that are made out of carboxylic acid derivatives. So we find our longest parent chain starting with the carbonyl carbon of the carboxylic acid. So we're going to start out with 1 here, right here, always. And then we're going to number through our highest number here. And in this case, it's 6. So if we didn't have the triple bond in there, it would be hexanoic acid. 6 carbons, drop the E, add oic acid. But we have the triple bond. So that means we have to drop the AN and add YN. But we have to locate it. So it's first is on the number 2 carbon. So that's how we have 2-ene oic acid, hex 2-ene oic acid. Okay, and then bromine is the substituent here on the 5 carbon. So we end up with 5 hex 2-ene oic acid. Okay. So infix, suffix, prefix, substituent every single time. All right, I got one more slide and then we're gonna break for the day, and it's naming esters. Esters are a carboxylic acid derivative too, and you'll notice that it has that electronegative atom, in this case the oxygen, okay? And you typically make esters from carboxylic acid and alcohol. So when we name them for the carboxylic acid we have, which is going to be this side of the molecule, the carbonyl side of the molecule. And then we add OATE, 08, to the name. And then whatever the alkyl substituent left over is, we name that as an alkyl substituent. And then our carboxylic acid 08. Okay, so let's apply that right here. So in this case here, we immediately know it's an ester because there's a carbon bonded to this oxygen here. There's not a hydrogen there. And we immediately know we want to chop that molecule right here. Why? Because that gives us the carboxylic acid on this side. Okay. So when we have that split over like that, let's name the carboxylic acid first. We have 1, 2, 3, 4 carbons. So that's butane, drop the E, and we add 08 because it's an extra. So butanoate, okay? Now we have to name the other side as a substituent. And we only have 2 carbons here, so that's the ethyl substituent. Notice that there is a space here. We do have a space when we name esters. So we have ethyl space butanoate, okay? So that shows you immediately, when you see 08, you immediately know it's the carboxylic acid ester. Let's see, I think that's okay. Yes, we're going to stop here and we're going to pick up on amides on Wednesday, and then we'll stop early and do our activity as a group activity in breakout rooms. So bring a copy of that with you if possible, or at least have electronic access to it so that you can work through it with your team. Okay. And then I, of course, give you the uploading answers to them. All right, great. If you got to go, go. And I'm going to stop recording and you can stay behind and ask questions if you wish.